Okay, I guess we can start, and we're really pleased to have Stephen Miller from Rutgers, who's going to tell us about what four gravitron scattering has to say about the unitary dual.
Yeah, so that will unfortunately be a little later. I wasn't sure who was coming, so I had to hear some different types of things. So let me talk about the unitary dual problem. Let's start here. Okay, so since I'm from Rutgers, I can ascribe this to a problem actually to one of my former colleagues. Who, I started thinking, well, it can't be that old a problem if I overlap for 8 years with this colleague, and I realized it's from the 1930s. And the fountain of youth is certainly in the Hill Center. I'm chair now, and I'm amazed by the longevity and activity level of my colleagues. I don't know how they do it. I guess by not being chair. Anyway, so let's let G be a group. Think of a real Lie group. Yeah. If you think you want time to stand still, it's a good way to do it. And so what we want to do is we want to describe fundamental unsolved question in representation theory. We're going to describe its unitary representations. So there's a lot of technicalities in the subject of what is a representation in terms of topologies and things like that. There isn't any meaningful difference once you have a good answer to that of several good options. So I'm just going to write it loosely. Okay, so we're looking at irreducible representations of G on a Hilbert space. Phi. And the key thing is that it preserves norms. Then, in case you're unfamiliar with the terminology, irreducible means it stabilizes. Well, you don't want the basic idea is that you don't want it to break into tethas, but there's topology involved, so it stabilizes no proper closed subspace. And then there are various ways to make the problem harder for yourself by reducing it to other situations. As a result of flow, it's very nicely described in David's book. So it explains algorithmically what to do if the group is not reductive. So you might as well assume it's reductive. Let's just go for the blood. The hardest case would be in a group as kind of as non-compact as possible. If G is a compact group, this problem is solved by Hermann Weyl. And the hardest case would be that G is split. And if you really want to be aggressive, that's the mother of all groups in some sense. Right? So Rawls used to say, you can do something for E8, you can do it for any groups. You'd just be able to write E8, something you can do for E8. They're very, life is more complicated than a mantra, but that's I'm going to get the result before you have to read. So maybe I'll just give an overview of the results and then come back and give some examples. All right, so let me mention the main result. And there are various pieces that go into this result, but I'm going to state something more general, which implies we've kind of been working on this in various stages. So this is kind of the state of the art right now. So it's a joint with Jeff Adams, Van Leeuwen, and David Vogan, who's here. I can't spell things today. So I want to sort of say this in a few different ways. Okay, so maybe just to give a little bit of a small background here, just as or not as a formal statement, but there's a key notion called a principal series. Principal series is an induced representation where you take B being the Borel subgroup, this is all being placed here. That's the notation. K will be maximal compact. So if you think of SLNR, this is upper triangular matrices, and then K is SLN. And then basically this will be from a character of the Borel, so of the diagonal part, and then there'll be, sometimes you write it, people write things like this. And then just give some background here. So lambda here will be something, I mean, it'll be in the weight space. This will be in the, make it R if you want. There'll be a sum of, these are the characters, and basically these are all the characters that are of the torus. This is an order 2 character. And then rho is half the sum of the fundamental weights. Sorry, half sum of the positive roots. It's the sum of the fundamental weights. Okay. So we can call this, I'm going to use this a lot, V lambda delta. And then Langland's early work on this described representations, the Langland's classification. And in this Langland's classification, you can think of representations as coming from different sources, and one big chunk of them, they come in general from things like this, where you induce from smaller representations called discrete series from bigger parabolics in the Borel. But in the Langland's classification, the things that are interesting to analytic number theorists all come from this family, like Moss forms. So there's a big piece coming from quotients of these. So this might reduce. And here lambda is dominant, meaning that it's pairing with it's pairing with any simple co-root is not negative. Okay. So this family is important because it's where Moss forms come from, it's where Eisenstein series, all the things that a number theorist like me would want to look at are here. And it's also interesting that these are the representations. There's another way to induce representations, which is much more complicated. It's called homological induction due to Greg Zuckerman. And these are things that are not homologically induced from something smaller. Okay, so the main result is let's say a conjectural description. Or, let me write away. It isn't making a conjecture. And when I put EA here, of course, that's just to show that it works for all the, up to EA, and we could do this for other groups that size as well. So let's give this set a name. Let's call this script L for Langland's. It's not. Okay, so in other words, this is the unitary representations that are not coming from smaller groups in the sense here. Yeah, okay. So I hope I can address more about this later. But if there's another extreme in the Langland's classification, which is where you take the parabolic to be the entire group, parabolic subgroup, and they're called discrete series. They're all unitary. So this is the hardest, I would think is the hardest direction, the hardest piece of it. But there are other parts that are big, right? So this is not the full unitary dual. Okay, so the description. Okay, so actually doing a description, I think it's actually okay. It's actually a full calculation of it, an explicit calculation. Now there's a small technical point. There's some fine print. Okay, and the fine print is something which can be dealt with, but not while one is chair. So July 1st, 2025, I'll finish this. Let me just explain what the fine print is. At some stage in the argument, you need to show some polynomials are 0. The polynomials are computable explicitly. I can do them in examples, and you see that they're zero, but it's a lot faster to compute them as floating point numbers. And if you put random floating point inputs into these floating point polynomials, they vanish to its high order, as the computer will show you. There's no way in hell that you'll have a non-zero polynomial vanish with random inputs. Right? I mean, if you're that lucky, you leave math and gamble the rest of your life, right? So anyway, so that's so that's the main thing we're working on. I come back over here. So let me mention some consequences of this. So one particular case. And so this is the case of delta is a trivial character, and these are called spherical principal series. Okay, so then, well, in particular, we have a description of G hat, and in fact, we have this thing called a spherical representation. A spherical representation means that it has a vector fixed by the Maxwell compact. So these are things that live directly on symmetric space G mod K without any bundles. Another way to say that is that I restricted to K contains a trivial representation. So this is called the spherical unitary dual. Is known for all split G, and this is the contribution here is for the exceptional groups. This was actually known by Barbosh and collaborators. Sequence of results. What they went out for classical G, and in all cases over the p-adics, and or any double A group of p-adics. I'm not going to talk about p-adics, but I just want to mention they have. I want to maybe say more about that later, so it's good to mention here. So one consequence of this is the spherical unitary dual problem. And then there's one more, which other consequence of this is there's a set of very deep conjectures of Jim Arthur. And these are arithmetic in nature, they have to do with modular form, but there's a local aspect to them as well. There's a sequence of unitary representations that they predict. Okay, so let me again a little more fine print for the lawyers. Right? I'm not handling, say, the complex form of E8 in this statement. This is for one way to think is this is for Chevrolet groups over R.
A couple of questions.
Sure.
What is the maximal compact of the eight?
It's a quotient of spin 16, but it's not. It's not. It's an order 2 quotient of spin 16, but it is not.
No, SS.
It's not SO88. Right? It's spin 88, spin 16, but it's not. SO.
It's
No, I said it wrong.
Yeah.
It's an order 2 quotient of spin 16. Yeah. But there's more than one. The fundamental group is Z2 cross Z2, so it's not the one that gives you SO8.
Okay. Secondly, what did you mean by order 2 in those?
Oh, okay. So let me explain what it would be for SL3 or even SL2, right? So Let me just change the terminology just a little bit here for SL2. I'll write the formula now. I mean a transformation, well, this is going to come up again, so. So here, this is, maybe I should use different notation for this.
Maybe right, not what I can.
That's a good idea. I'll do it over here. Okay. Okay, so I want to look at this. Okay, I want to look at functions from SL2R. Just accomplish numbers with the transformation law. That it transforms on the left by the Borel, the upper triangular matrices. So here nu is a complex number. Eta is a parity, so this is my 2z, and this eta is that delta, basically there. So it's really a character of the diagonal elements.
Oh, I have the two you just meant it square was one.
Yeah.
Oh, yeah.
Quadratic, yeah. Okay.
Context.
Okay, no, that's, you know,
Yeah, no, okay. So,
you should always assume that if I'm saying anything about algebra, it's the simplest possible.
I know, yeah.
Answer. You can't generate complicated things. Okay. Right, okay, so now at least I go back to the original. All right, so these are the main results, and one thing that's also part of this, which it's not quite the right time to do it. We have a description of what the unitary dual looks like for many groups, modulo some statements that we haven't been able to prove. This is a computational statement that relies on me for a theorem. That is not all done for E8. We were just discussing this upstairs. I mean, you could very generously say maybe it's a quarter done, but I think that would be misleading. It's probably much less than a quarter. But it's really, I think, a significant positive fraction. Right? Probably, I don't know, 10%? I don't know. But it's going to take a while. But for E7, this is something which we just said runs on this laptop in 20 hours or something. So there is a
20 days.
20 days. Sorry, 20 days. Okay. Okay, but it ran, so it's done.
Yes. Your house.
Yeah. It's very well put. Yeah. We haven't measured the carbon footprint of the injury. Probably get it right. Okay. Okay, so one thing that made this problem hard is that up until now, there wasn't a conjecture, at least, in general, for what's unitary and what's not. And so that I'm not really that's something which is kind of intricate. I don't want to go through that, but all right. So let's talk about. I want to give some examples. I started drawing some things over there. Let's come over here. So I just want to go back now. The results.
By the way,
Yeah.
Steve, you said quite correctly that there's no conjectural answer which would have made life easier. But one of the things which is almost true, which is sort of nearly a consequence of these calculations, is that all of these spherical unitary representations are nearly deformations of Arthur's unitary representations.
So, in fact, there was a conjecture for the spherical case because the Barbosh and his collaborators, when they prove this for p-adic groups, have a method that rules out things from not being unitary, and it applies to real groups. The problem was to show things are unitary. The techniques that work in the p-adic case don't work in the real case, but they conjectured it would be the same set, and they were exactly right. So, but it also happens that the Arthur points nucleated pretty well. Actually, maybe when I draw G2, since you're here, you'll be able to help me with that. Okay, so let me draw for SL2 and then I've got, maybe I'll move the camera over, I'll tilt it or something. There's no way I'm drawing that again, it takes me forever. I literally practiced this for a few times. Okay, so let me give an example. This is really the prototypical example. Because SL2R. And this was done by Bargman, a physicist, 1947. Now, Galfond came from the point of view of dynamics. Bargman came from the point of view of quantum mechanics, where unitarity is very important. And we now recognize unitarity is important in its own right, but it's also important in automorphic forms. One of the definitions of automorphic forms forces you into the world of unitarity. You're not forced to be in that world of automorphic forms. There are plenty of interesting ones beyond it, but it's really been a major technique to. And the most famous example is Langland's Shahidi method to Henry Shahidi and Kim rules out poles of L functions because otherwise it would contradict results on the unitary dual. Okay, so we have these principal series. He gives a complete description, in fact, of the representation theory of SL2R using principal series. And it's what does that involve? Well, this V nu eta, and it's usually irreducible. So first of all, he studies the reducibility. But it's reducible unless. Okay, I'll make an equivalent. Unless you're kind of unlucky and land at some integer points that depend on the parity, you get something irreducible. I'll draw some pictures of that. So there's two cases. One where this is a spherical of unitary dual case, where it's trivial. Wait, slightly doing that, and then I'll draw split screen. I'll draw it right in front of the camera, so none of you can see it. I'll make it high. Okay. So let's try the new plane, complex plane. Well, the reducibility happens at half integers. There's a duality between V nu and V minus nu, so the picture on the left is kind of flipped from what it is on the right. But what happens when it reduces here? Well, here it reduces and it has a trivial representation as a quotient. Meaning that there's a subspace of basically a discrete series. I'm oversimplifying slightly, but not much. And that space is invariant there. You can kind of tell from the formula here that minus nu, this character is trivial, so it makes sense the trivial would then be a subspace. So here the trivial is the subspace, and then the quotient modulo the trivial representation is discrete series. And then it's the same type of picture over here with one exception I'll mention. Here you have a finite dimensional quotient, and then you get more discrete series in subspace. Actually, I have color, so I want to maybe strategically use the color. And then, on that, I'll just draw the picture over here. But now it's a little bit different because now the reducibility is at integers, including 0, which. And so again, you have the same type of picture, finite dimensional quotient. You want to do discrete series subspace. Okay, so these are all the representations of SL2R and all the irreducible ones, of course. And now we can ask what's unitary. So that's why we can this Mountain Dew colored chalk. Those of you that can collaborate, you can calibrate your monitors at home. Get Mountain Dew. Yeah. So the induction is built, there's that half there, but the half is very convenient for a lot of purposes. Oh, by the way, here it reduces as limits of discrete series. Yellow is going to be unitary. Right? So this thing is built to be unitary on the imaginary axis because the character nu is imaginary. But maybe the most salient feature, the key takeaway from this is that this unitarity actually extends in this range up here. Okay, and it extends to the trivial representation is the only finite dimensional unitary representation. So this is the key thing. The one thing to remember about SL2R is unitary dual, it's a complementary series. And in fact, that's true in the deeper sense that discrete series are unitary for a clear reason. They occur in L2 of G. Once you're in L2 of a space, you have a unitary structure. Trivial representation is unitary. And the things on the imaginary axis are kind of obvious, but this is maybe a bit of a surprise. In fact, this unitarity bleeds all the way to a half. Unitary set is closed. So you get a nice proof that the trivial representation is unitary, which one thing I learned from David is that thing you should never discount because it's unitary, from many points of view, the unitary representation is the trivial representation is the hardest representation to show as unitary from certain vantage points, not all vantage points.
Langland's vantage point.
Yeah. It's really the Atlas vantage point, right?
Sounds like a koan.
Pardon?
It sounds like a koan in Buddhism.
Oh, okay. Okay, well, I'll get to the more theological aspects in a second. Maybe you can summarize it. So actually, there is a reduction that reduces this to real nu. So real nu tells us the full story. It's easy once you know it for there. So we only worked up real nu or real lambda when it had principal series on the board. And so now you can just summarize it that if eta is even or odd, the unitary dual is my color code. Here's that nu is an interval from -1/2 to 1/2. And here it's just a single point, it's just 0. Now, there's again a modern point of view which even makes that kind of obvious, which is that the point 0 is definitely unitary. And there's a principle that as long as you don't mess up the representation too much, you can't ruin unitarity. It can be deformed. So there's notions of signatures. So you have let's say there's a Hermitian form, you need the signature to be positive definite. The signature is a holomorphic function of nu, where aside from when the representation is aside from places that are cut out because of reducibility, or more accurately intertwining operator singularity. So that's something that's known in general. And so once you have it at 0, you have to have it all the way in this region up to 1/2. And you get it 1/2 by this extension. Right? The unitary dual is closed. So this topology in geometry buys a lot, and that's one reason we're able to prove these theorems. Okay, so this would correspond to the spherical unitary dual. as you can see, the spherical unitary dual is, it's most of the story here. Right? The only part that's not subtle is that this complementary series issue. Once you understand first what discrete series are and things like that, which we do.
I'm sorry, you're not drawing the discrete series here in your.
No, I was sorry. I was just trying to draw the plus discrete series, plus trivial plus discrete series. Thanks. So the analog to the theorem that I wrote down about things from the Langlands classification. This is in the set L. These are things, again, the Langlands classification that comes from Morel. So the only split G where the unitary dual is fully known are these two examples. And I want to show here is the spherical unitary dual in these examples. So I have an example here for two examples. The first one is for G2, and here the Deacon diagram looks like this. There's a long root and a short root. And the unitary set, maybe I didn't draw this one so accurate. Okay, the unitary set is a square plus a bunch of other points. There's a Weil group symmetry here. Rho, this is rho from before, so it's 2 alpha plus 3 has beta. And there's 8 common 8 points to it, right? Now for G2, this is worked out by Vogan, which I'm not sure who first did this. But it's nothing. David. David being it's easy to remember who it is by the diagram. See in a second. And when I came to visit you like 10 years ago, you made a comment that this is about 2/3 of the unitary dual for G2. So that fraction, 2/3, goes down a bit as the rank of the group increases, but it doesn't decrease exponentially. I'd say it probably decreases. Well, if you want to make a guess, it's probably 1 over the rank, from the experience we have. So I'm just making up. But certainly here, this is the key case. Okay, so here's the Deacon diagram. It's triple bond, so a long question. And it's center this. So now that I don't believe how many times I've had to try this and still never. Back to Ezra's question. So, this row is where always where the trivial representation was. And there is a row up here somewhere. Up here maybe. So row is trivial, and then once you have it, you have a bunch of other 12 of them. This is definitely not to scale, okay? So we had this principle before that once your unitary, it kind of bleeds out. So the middle is unitary, that corresponds to 0.0. So this entire region in here is unitary up to and including the edges. Now, what's highly interesting here is that it goes up to here also. So, it makes sense. If you just, there's some reducibility here, some reducibility in the representations. The signature changes, but then changes back as you go down. Okay. Now, there are other reducibility all over the place further out, so it's kind of special that it stops here. Oh, sorry about it. Hey. I'm not very practiced in drawing diagrams like this, but this shape apparently looks like something I've never drawn before. But that's this, we call it the star of David. That's a great. So I'm gonna come back to that picture later. Actually, I'll come back to it. I'm going. Let me do it now so you don't have to turn the camera. I mean, I've gone so out of order. I don't even know. This is a decorative. I might as well read from the back. But I want to point out. I want to point out something about this picture. This picture looks like a nice kaleidoscope, right? There's another way you can view the picture. There is a symmetry. So actually up here, this is the first fundamental weight. This means if you pair it with the co-root associated to alpha, you get 1, but if you pair it with the other simple co-root, you get 0. And then there's a second fundamental weight, which goes up to about here. This is it's perpendicular to this alpha. You can see that's a 90-degree angle there. Good order. This shape is going to be really relevant in a minute. But in a way, it's just two regions. What's that point? It's just propagated. So, this is something that doesn't appear to have any, right? And the point is across the right place.
So you're drawing a different fundamental domain?
But actually, this is the positive chamber.
Yes.
Yeah. So in the positive vial chamber, you just,
This 30-degree cone is the vial chamber.
Right.
yeah.
Right.
No one knows it's Jewish. But but once it's propagated by the mirrors, it looks different, right? So, but it's a lot simpler to describe in terms of this area.
I don't think your omega 2 is right though. Or
It's too
pi
big.
2, is it? It's that funny bear pi.
Yeah.
Because it's infinite with the long root should be 1, and therefore it should be
So the co-root,
root.
yeah.
Okay.
Okay. So this region that I've just drawn looks something like that. We gave this a name. So this is these are the fundamental weights, and so this region we call the FPP, which is fundamental. Parallel pair. This word's long enough.
We disagree about the middle, about the penultimate E.
Oh.
I'd rather not.
I had this discussion with Michael Harris again, and we concluded that it depends, David and Michael and I are all products of the Pennsylvania public education system, and David's the only one who graduated. You got a degree somehow, and I never even got that. But we didn't have enough gym credits. Or in my case, also didn't have enough English credits, which is probably more relevant. Anyway, so this is the fundamental. This is a parallel pipe that stand in a way by the fundamental weights. It's a set of combinations of the fundamental weights where the coefficients are necessarily non-negative because they're dominant are between 0 and 1. That's a key thing. And so now, why is this important? Well, think about how much smaller this is. In principle, I mean, there's a general bound. I mean, David can give you ways to cut down on this, but as a general principle, there is an a priori bound on the eigenvalues of Laplacian for Mott's forms that would correspond to this whole ball. When you start dealing with representations that aren't spherical, you have to worry about other parts of this fundamental chain. Now, I happen to know what the volume is of the balls in 8 dimensions, and the ball is radius is the norm of rho. Has volume bigger than 599 billion. I don't remember the
Going
number.
back to E8.
Yeah, for D8. Yeah, for D8. So this is one reason why sphere packing is cool there. Okay. Whereas this chamber, it's the determinant of the Hartman matrix, 1, 2, or 3. In the case of E8, it's 1. So that really cuts. If you can prove a theorem that lets you restrict to this FPP, you gain a lot. you gain like a trillion, a factor of a trillion in some sense. I mean,
In fairness.
There's a lot of fairness to
Divide that volume by the order of the violence.
well, that's the thing, for these other characters, you can divide by something, but it's not,
No.
it won't be, it probably in the hundreds, right? Right? Yeah, this is an unfair comparison. Also, David can give you better inequalities. But just to give a, the a priori principle that there's a lot of, it doesn't look like there's that much space. The question is how much extra space is there here? Here there's not that much, but it just becomes very, very big. Yeah, if you divide that by 700 million, then you're down to like 1,000, you barely saved 1,000. But still.
Factor of 1,000 here, a factor of 1,000 there,
Yeah.
pretty soon you're talking about.
Real money. Right. Okay. So another way to describe this fundamental parallel pipette is these are the, I had before this a star, this was the weight lattice, these are the reals, these are where the characters live. And these are the ones where just the pairing with simple co-roots between 0 and 1. Another way to describe it. Astronomers use these equatorial mounts that track just aim it at the sun. So let me mention there's various conjectures one might make about the FTP and unitary. So let me start off. So there's a theorem, and this is due to, well, I think it's, as far as I know, it's due to Garbach and Garbach alone, but there may have been collaborators since it's older. So this has to do with the spherical unitary dual. Any with a unitary quotient. And so here in these statements, I'm going to assume lambda is dominant, meaning those inner products are all these positives, how big they are. Because lambda in the FTP. So this is the spherical case. How does this proven? I mean, there are various ways to prove it. I think the way, as I understand that he did it, was he has a very powerful tool to use this, which is the spherical, which is there's a heck algebra techniques, and he can compute the signatures. So I think these techniques can be extended to other situations, but I mean, maybe what I'm doing is that in fact, but I have other techniques, at least I think are different techniques which I'll mention in a second. But that's an obstacle, is that in the spherical case, this calculation is certainly a lot simpler. Now, so this is we have in this case, and this is where I had that asterisk about the calculation with the floating point values. A very minor point, but I have to be honest about it. It's the same conclusion. And let me just state it for G, E, E. We've only looked at this really seriously for exceptional groups. By the way, the unitary dual is of course known for SLNR. I should have said that. That was David proved that in the 80s. Yeah. Same conclusion, but let me just write this down. but for so now one would like is to have reduce the assumption that it's a trivial character. This is the non-spherical case. So there, we can do this for anything. You can do it for EA. We've written this out for E7 and so forth, but there's no general. This is still has to be ironed out. This is the basic idea. So again, there's that restriction to this FPP. So this bounds the size of the unitary dual in a way which means it's only several hundred factors. Okay, so then the idea here, the main idea is so the theory of asymptotic intertwining operators. And this is motivated by Wilfred-Schmidt's work, so it can't be here not to mention Wilfred. VHS, variation of Hodge structures. And so he does in that work is he looks at the Hodge theory on annulus, and he changes the parameterization of it so it basically gets deformed to the circle's touch, and he proves following a conjecture of Deligne, but there is a limiting Hodge structure there. That's not what's going on in this proof, but that's the motivation. Is that there's an asymptotic structure to these objects, and that asymptotic structure it can show that things are not unitary very far away. And then there's a game of coming back as close as you can to the FPP by testing it on very, very explicit representations but not so small representations of the maximal compact. So there's a 1920 dimensional representation of K for E8. That's this N16 example. And in that example, it sort of doesn't know about other reducibilities. So the rough idea is that if you're way out here, you know that it's not unitary that far, and you have free passage up until you hit a border checkpoint. And then, there might in principle be other checkpoints that could stop you, but because we have very explicit control of this 1920 by 1920 size matrix, you can get all the way up to where we need to for each wall. So you have to look at each parity, and you have to look at each wall and show that there's an asymptotic limit and that there's no guard standing to get there. In fact, you can get even further in many cases. So for some different parities, the picture it's always going to include this region here, more or less. It's less than, I guess it can only include it will be something like this in general, depending on how far it leads from zero. But there are some examples where this is a hyperplane, this hyperplane here, you can get like all the way down to here, and it cuts out other regions. So these are all things about non-unitarity, but non-unitarity is in a way is at this point the issue, I think. And then there's a more general principle, which and this is David's version of this, and so it's the following. I wrote down. Well, if I can just say it. Okay, so any reason. I'm trying to put this way. Should have prepared it. Any useful representation of G with so this lambda thing in general is the infinitesimal character. Dominant, no system is dominant, right? but not in the FPP. So this is more general because what I was talking about before were things that came from quotients of principal series. These could now involve discrete series. Has it's unitary. I'm not sure what you would say. Unitarity status has unitary status determined through cohomological induction to the smaller group. It's okay? Do you get this statement? Or good? So this theorem is an example of that principle, but it's more general because it looks at other types of representations. And what does this mean determined by? Well, there could be some smaller group. It might not be a subgroup, it might not even be split, or anything like that. But there will be some representation that all the things that are not handled at this point are things that are cohomologically induced. And so you can check what is cohomologically induced from, and if that thing is unitary. And there's a certain parameter to it, which is if it's in a certain range, then you know that unitarity status both up and down. The elevator works both ways. And so the idea is that that's how it's determined. You can read off whether it's unitary or non-unitary from knowing the description of it. So if this principle were proven, and if the computation of everything within the FPP were complete, this would solve the unitary dual problem, because it would be a statement modulo of smaller groups and a fairly simple criteria that can be tested very easily. That computation was what I was referring to before. It took 20 days for E7, but once it's done, it's a list and it's there. So the goal will be to prove this, right, and make the list.
Sorry, isn't it the argument you outlined, because not everything there would be logically induced?
Yes, so there will be. So there are various theorems like this that if lambda is big and the representation is unitary, we know why it's unitary. And so there's sort of
Name or point to such a theorem that they can.
so Susanna David Copley's name, yeah.
Susanna Salamanca.
Yeah, so she has a theorem that it's bigger than the FPP. I think it would correspond to it's slightly like maybe that one becomes a 2 or something.
If the infinitesimal character is dominant and has the property that when you subtract rho, it's still dominant, then she gives a complete list of such unitary representations.
That would be we have here. But it's the same. There is a principle like that, and the idea is possibly that principle can be extended down to just to the limits of the FPP. This is the type of thing that only shows up, starts really getting nasty for big groups. Like for SL2, you don't see anything like this. You just see the discrete series, and yeah, that's pretty simple to handle. It's from a character on a torus, a compact torus. Okay, well, it's already. How much time do I have? Like, am I done? Or
5, 7.
okay, that's perfect. 5 minutes. Okay, let me mention string theory. I kind of emphasize this because the people I recognized were not string theorists. And okay, so why am I talking about any of this to begin with? Well, there's something pretty ridiculous that happened in nature. Maybe not in nature. So there's Michael Green, like the Green Schwartz, and I'll put Pierre Vanhove. There's some other collaborators. They were studying certain types of Feynman diagrams, and they studied the scattering amplitudes. 4 gravitons. So here you have, this is the most basic question you can ask is what happens if particles don't interact and have anything to talk about. So if 2 gravitons hit each other and something happens and 2 go out, which you can just think of as 4 coming in also through their symmetries. Something happens after that. This is the crux of general relativity. So Einstein GR predicts, I mean, there's some formalism in terms of contractions of Ricci tensors, some term. And then the low energy limit, one brand of string theory, which I can say more about, posits that there are correction terms. But these are non-perturbative correction terms in their language. Now, there's supergravity, which, so, Green and Schwartz introduced supersymmetric string theory, but the super part came in earlier in the 70s. There can be functions on groups that come in also. So the next term involves a derivative of these. This is this kind of basic Feynman diagram language, and then there's some coefficient here. They call it E00, and this phi, it basically it describes basic parameters of the theory. So the way I understand it is that, let's say you have some control room and you can just move Planck's constant up, right? And the world would just become very bizarre, and then you move it back down, and things are back to normal, right? There's a whole bunch of these moduli of the theory, and these naturally live in a split form E8. I mean, D is big enough, but what's D? Here in this version, this is type 2 string, type 2B, or type 2, I guess. Just type, no, I forgot already. I wrote it down. And they compactify up to 10 dimensions. So here this is compactified in the simplest way, which is with a torus, by a d-dimensional torus. So the space-time dimension is 10 minus e. Okay, now, so that means there can be some interesting functions on Lie groups that come up here, just even in this next term. And that's like to calculate it, because there's a whole classical theory about Virasoro amplitudes and Veneziano calculations and things like that are pieces of this. This is kind of like a group completion of a very classical picture. And so in the string world, there's also gamma invariance on these functions. Now, in other words, they're talking about the same function, but string theory has dualities in it. And U duality, this is the same U duality that gives mirror symmetry. In this context, insists that the scattering amplitudes have to be invariant under a very large discrete group, which is basically the integral points of the Chevalier group. So that means that these curly E functions, like E00 here, is automorphic. Okay, there's a whole bunch of these. Any type of problem like this, they're going to have a whole bunch of symmetries being looked at. Okay. All right, so this formula is correct without explaining. Now, there's a lot of these things, and they're not all interesting to number theorists directly. But it also has, there's a.
Is there a way to state just what the right-hand side of the board says? The theory provides you with one automorphic function that has a specific.
Well, there'll be a few of them, but yeah.
A few of them depending on some into.
Yeah, let me write down the next one.
0, 1.
Call it whatever I want. Okay. So these correspond to this work of Doker and Fong that computes loop integrals, and that's be like a constant term of these automorphic objects. These are like an automorphic completion of those calculations. Another way to say it is that there's a whole bunch of things that come up, like all these loop amplitudes and instant time terms, and if you add them all up, they give you something that's modular. That's kind of a fancy, that's kind of like a more suggestive way of saying it.
Are they automorphic functions or automorphic?
Well, that's exactly about to say. But at this point, they're just automorphic functions.
So is this a looping, so this is zero loop, one loop, two loop?
Yeah, yeah. So that's an automorphic function. Now, but this theory assumes the maximal amount of supersymmetry. And that has manifestation. So these interactions are protected from some perturbative corrections. And so basically there's a certain what they call fractional BPS state. And this means that certain differential operators act as scalars on them. And now it sounds like an automorphic form. So they satisfy certain differential equations. And so now it's not just an automorphic function, it's an automorphic form. But that's something that will stop after here. The next term after it is no longer automorphic. So now we have an interesting automorphic form. How do we figure out what it is? Well, there's a lot of background and information about this because there's all this work on loop amplitudes. And a key idea is, well, this is compacted by a torus, and that torus may have very different, I think it was quoted by square. You might take one axis and stretch it really, really big. If you stretch it to infinity, it's like adding an extra dimension to space-time. You can't tell at some point, right? And so they can take that limit. And so there's sort of three limits that come up. So there's decompactification, this is what I just talked about, decompactification limit. Okay, so here's one large torus, these big language. Another limit is it's called string perturbation limit. Actually, there's a bunch of different, I'm thinking of EA, there's actually 8 different limits, but maybe the one that's easiest to understand is it's called the M-theory limit. And here they can approximate with 11-dimensional supergravity. So the point is that anytime they do this, they're kind of they're looking at some different object and they understand maybe inductively what's going on with that other object. Now these correspond to 3 different parabolic subgroups of E8, general ED. This is now, the Levy factor is ED. Here the Levy factor is spin ED. And here it's sub B. Actually, S is equals 1. S is equals 1. And this limiting, well, when you have an automorphic form, you want to know its limiting behavior, there's a theory of the constant term. So basically what happened is Green comes to me one day and says, if you look at this object and you look at its constant term, it's got to look exactly like this. There's Riemann zeta functions, all sorts of nice pieces of number theory. It's very, very precise. And so piecing this together, the only thing that it could be are Eisenstein series. So this is in fact an Eisenstein series. Okay, it's a realization, in this case, of the minimal representation. That's known to be unitary. I've done it's not been worked on that. But the one right after it, I think I like to say this was on David's list, this was most wanted to show as unitary. This is, and it's very hard for other methods to show as unitary, and I mean it's not purely a consequence of this asymptotics, but it's very related to it and to the machinery built to put this together. So the upshot was Michaelis has a book on Eisenstein series and he does a computation for G2. And he writes a comment that the calculations are long, but the reader is encouraged to persist because it'll all cancel in the end. And he said, I don't know why. So Green comes to me with it's like an E8, but the value instead of being order 12 is order 696 million. It says there are gonna be 2 terms left over, and here's exactly what they are. He's right. So there's some very deep stuff there. This cow stops giving milk after a few examples, but there's gotta be something else. There's gotta be some gold down there. Questions?
I was a little confused by your 1920 dimensional representation. I didn't quite follow how crucial it was to the story.
Okay.
Because I don't have Sage with me, so I can't confirm this, but it looks like it's the 16-dimensional Rita Schwinger, the Gravitino. So it's like a Majorana spinner, Majorana bar spinner tensor with the vector representation. And then reducible, and that is a 3/2 spin field. So, but we're not doing.
You're worried it has to descend to the.
Well, we're not doing physics in 16 dimensions, so I don't know what that could mean. But,
Well, spin 16 has 2 different 1920 dimensional representations. So one of them, I've got it over here. One way to get it is this way. It's like this, the other way is
yeah, exactly.
the other way is like this.
Yeah, exactly.
This one, I'm gonna take set up. One of them,
One of the orientation of 16 dimensions.
Yeah. the way the depends how this maximal compact fits inside E8,
Yes.
right? One of them doesn't descend down to this order 2 exposure, the other does.
Yes.
And so one of them, in fact, if you see the relevant, I made this mistake, I obviously I picked the wrong one first, right? I was expecting to see integers here, where these walls are,
Right.
and so I have integers,
Yes.
and I it's wrong,
Yeah.
it's all wrong, then I realized another one, so then, and then,
Yeah.
yeah, so one, I can tell you more about it, I think that was what you were asking about, was why is this half versus.
Oh, because it gives those integers.
Yeah,
That's why you.
these 2 are equivalent, if you just think only about spin 16, this is
Right.
diagram automorphism. But the way spin 16 sits inside E8 favors one over the other.
Yeah, but it exactly corresponds to an orientation of 16 dimensions.
I think so, yeah.
So it's, yeah.
Actually, probably the other 1920 has a similar role to play in the principal series for the double cover of the A.